All right. Well, save your applause till you see what's in store. Like Boris said, I'm a cloud solutions architect at Google, working in media and entertainment, and I spent about 20 years working in visual effects, mostly on the pipeline side. So the one line that I use is, my job is to figure out how to do all that on the cloud. But sometimes it's a little hard to figure out exactly where to start. And we're going to go through some interesting machine learning concepts today, but I want to give you a little bit of an overview. Has anybody here done any machine learning, any API stuff, or TensorFlow? TensorFlow, anyone? All right, okay, good. To start with, there's this concept of a model that you build yourself, or there's what's called a public API. And the public API on the right-hand side, those are essentially pre-built models that you can use to do things that you use every day. Like on your cell phone, if you've got Google Photos app, you can search by a tag. You could search for a dog or a car or a person even. And that's using something called the Cloud Vision API. Not necessarily for Google products, but you can access these APIs as a customer. There's also things like the Cloud Video Intelligence API, which lets you identify things in videos. And these are all great. But they're really only returning a strict set of labels and tags and metadata that you can use to apply to your assets. So how do you customize that? How do you build a completely different model? And to do that, you use the tools on the right. There's a couple more, but these are the basic ones. TensorFlow is an open source language that was developed in part by Google, and it's freely available, and it runs on any platform, and there's Python APIs. I wouldn't say it's easy to get up and running, but some of the basic training models are fairly simple to follow. And then there's also more elaborate workflows like AutoML, which allows you to take the existing APIs and extend it with yours. So let's say, for example, you have you're a company that has a bunch of products, and you want to be able to recognize your products in images. Well, you could use the AutoML to extend the Vision API model. But anyways, I'm not going to get too deep into our products because I want to keep this as a high-level overview of what machine learning is and what it can do. So has everybody here seen this saying, right? Pick two. It can either be fast and cheap, but not good, or cheap and good, but not fast, etc. So why not have all three? Why not have a slider that you could just say, for this render, I want the highest quality, and I want to lock down time, and price can float. Like you could lock and unlock any one of these. Let me just step back to show you. And this is a concept I came up with. This is not, in practice. Obviously, you could see I used a simple wireframing tool to build my UI. But just to give you an idea of what machine learning can do for render resources, you're basically predicting with certain levels of confidence how long something's going to take to render, or what kind of resources, or how many CPUs something will take. You can lock and unlock different factors, like what kind of instance you want to say. I want to use a minimum of 32 cores, and then it'll sort of solve for that. Or you could say, make the resolution scale float so that if you pump all three up, like you set the quality high, you set the time all the way down, you set the price all the way down, well then your renders are going to be this big, but maybe you want to get a bunch of postage stamps, right? Or you want to get a bunch of thumbnails. So let's move a little further forward. And yes, it is 9:10 in the morning, and we're going to go over machine learning basics from a mathematical perspective, and I apologize, but this is going to sort of give us an introduction and give you an idea of what a machine learning neural network can do. And just gives you sort of a taste, and then we can go from there. And also, bear in mind, I am not a neural network expert or machine learning expert, so I'm going to give you a high-level overview, not just because, again, it's 9:10 in the morning, and this is total chaos, but also I don't know everything that these researchers have come up with, and some of my colleagues are doctorates in machine learning, so I don't want to touch any of that. But okay, so You might have seen this board before. It's a variety. It's a sample set of around 60,000 handwritten numbers from 0 through 9, and that's a training set that we use. And each handwritten digit is exactly 28 by 28 pixels, and it's grayscale. So this is sort of like the simplest scenario to do an image-based training. It's called the MInst data set. And the idea here is to get from the left-hand side to the right-hand side. How do you give it a digital non-definitive image and spit out what it thinks the result is? And the way that a neural network works is that it's going to examine the pixels in the image, and it's going to iterate over and over and over until it comes up with what it thinks is the most accurate result. The process of training, however, is a little different because you're actually telling it what the result should be, and then it'll train it against that, and until it achieves that result, it'll keep iterating. And once it achieves that result within a certain tolerance or a bias, it'll store it as the result, or as it'll store the bias. So basically, that's what's called the model converging. So let's look at the image and let's figure out how it does this. So we take an image of 28 by 28 pixels, image of the number 8, and this is the simplest type of model that uses these neurons. The neurons are the circles on the right-hand side. And essentially, what we're going to do is we're going to try to identify this as the number 8, and we're going to break it down into 784 pixels, and we're going to linearize those pixels. Because it's grayscale, it makes it a lot simpler. We'll get into the whole RGB value factor a little later. But what it's going to do is it's going to connect each of the inputs. Each of the 784 pixels is an input. It's going to connect each of those to a neuron. And what it's going to do is run it through a whole bunch of math. But it takes the grayscale level, and it calculates it as a total sum, and then it applies what's called a bias to it. And the bias is in that sigmoid function down there. And a lot of this is going to go over everybody's head, including some of it, including mine. But what's going to happen is it's going to calculate a sum for this image, for this number, 7,840 times, feeding it into each one of the neurons. And each one of those neurons is going to store a bias result for it, right? So the bias will hopefully be low for numbers 0 through 7, and higher for number 8, and lower for number 9, right? But you still have to train it. And this model really only gets you about, I think, 92% of the way there, or something like 90% of the way there. So this is what's called a flat model. The classification is also known as a softmax classification. So essentially, you have the sum total of all the 784 pixels with the neuron outputs, and the weighted sum results in the softmax calculation. And in this case, have we achieved success? Well, the top line there is what they call that's the training data that pushes through the correct result, or it's assigning the correct result. And actually, I've got that wrong. That should be a 7 because it's no, never mind. And then the computed probability at the bottom here is, so this did work, all right? Or at least in this simple example, did work. The training model, and this is something you could run with I think it's done with MATLib, this animation. Can I go back and play that again? So what it's doing is it's running through an entire data set, a training set of, I think, 10,000 images. And the red part on the bottom right, that is, those are the digits that it got wrong. And then the training digits up at the top, the red is what it got wrong as well. So the goal is to get as little red on the bottom as possible. And you can see there's a bunch of different metrics. On the top right-hand side here, I don't know if I can get a pointer, but on the top right, you could see the accuracy. It's cut off by the screen. But the accuracy is, the training accuracy is not reaching all the way to the top. So it's only getting to around, I think, 90%. And then there's this thing called the cross entropy loss, which is right in the middle there. And that's very, very noisy, and they try to get rid of that as part of the testing process. So this gives us a 92% accuracy rate. That was only a single layer. If we apply this, what's called the deep neural network, we can go down multiple layers, and we could take the sum, we could do it once, take the sum of that, and then run it again and again and again, reducing down the variance until you get to this softmax down to this level 10 here. And that still gives us 92%, which is kind of curious because it's iterating over and over. So they're asking what's happening. And scientists have basically, researched this for many years throughout machine learning, and they've come up with an idea that there's something called ReLU, or Rectified Linear Unit. I've peppered a little Simpsons references in here. I hope you don't mind. But and this is something that researchers, for some reason, are very excited about discovering, even though it looks drastically simple. And that's basically, instead of using the sigmoid function on the top right, they clamp it anywhere less than a value of 0 for a result, and it's just a linear a linear unit function from 0 through 10. And the code at the bottom, that's actual TensorFlow code to run this computation. So if you use this rectified linear unit to calculate, you get a much better result. You get 98%. And you could see, the accuracy on the top the top left, maxes out at 100%, and you get the 98%, the red line there. And this cross entropy loss, you could see it's almost, I wouldn't say it's gone, but it's much less noisier. So this still isn't good enough. This is, if you think about, the post office going through postal codes, it's going to get 2 characters out of every 100 characters wrong, which is unacceptable. Humans can do way better than that. And the best model out there can do 99.77% accuracy, something like that. So now we have this grayscale image. How do we expand it to an RGB image? Well, we have to add what's called this convolutional layer. It's deep neural networks are akin to convolutional layers in the same way that 2D versus 3D imagery it's analogous to 2D versus 3D imagery. So with a convolutional layer, you take multiple inputs and you can almost step left and right and back and forth in 2 dimensions to what they call the stride function, and break it down to achieve higher results without using taking each pixel and laying it out on its edge. You're basically taking a 2D image because the contour of the imagery is what's important, right? That means that you can get an even higher result because now it understands the contour. It understands an 8 that looks like an 8, taking the sum of it all, and it's testing against it. So, all right, I know that was very dry and boring, but how do we use this in production? So, we need to be able to do, we're going to focus on 3 things in this talk. We're going to predict resource usage and computation values and factors based on certain functions, based on certain historical data. We're going to learn from that data, and then we can use it to improve our model. So also, thank you to Kevin Margaux, who's right there, yes. This is some of his data from Construct, although I've mashed some of the shaders, and I apologize for that. But it's so small you can barely see it. So let's look at a sequence of images here, and let's again, these numbers they're just fudged, so just pretend that they're actual numbers. But let's say it's a 100-frame sequence, and the frames at the beginning, there's no characters that you could see. The motion blur is very low, and towards the end, there's lots of motion blur, there's lots of camera movement, and it takes longer to render. And let's pretend that it takes more memory. I mean, 200 gigs to render a frame like that is kind of ridiculous, but let's just suspension of disbelief here. So what if we could use machine learning to normalize render times? What if, this shot here, if you send it off to the render farm, frame 1 is going to be back in 22 seconds, but frame 100 is going to take 2 minutes to come back. Big deal, 2 minutes. But let's just say it's 2 hours versus 10 minutes. What if I wanted everything to come back at the exact same time so that I don't have to wait on the final frames to return? can we use machine learning to normalize the render times and to basically predict how many cores a render will use? And that's simple enough to do based on historical data. If you've already rendered this frame before, you can get an idea of the memory that was used and how long it took, and then you could sort of use that as an input function to multiply the number of CPUs. And I say vCPUs here because we're focusing on cloud. This is most easily done on cloud, where you don't have to deploy one big machine and then bin pack it. You can deploy one machine with the exact amount of RAM and cores and GPUs, whatever number type of GPUs you want, to spin up to render one frame or a chunk of frames, and then it goes away when it's done. And that's a sort of a more dynamic resource usage model than what a lot of companies are doing on the cloud. And we're trying to work on, at Google, we're working on different ways to deploy jobs to the cloud so that you don't just spin up 400 virtual machines and just stuff them with renders until they're done, and then some sit idle and some work for 24 hours. Can you use resources on an as-needed basis? So in our sort of figurative UI here, to achieve that previous frame to flatten time, you basically want to lock down time. Unfortunately, I don't have like a little lock icon on that slider, but you would lock down time and say, I want it to be done in exactly this amount of time, and then you would unlock the minimum instance type so that it could vary to assign it whatever you want, or whatever it deems necessary. And you'll notice that these are not values you can change. These are values that the model would determine. It would say, oh, I think this is going to take this many render hours, and it's going to cost you this much. Obviously, that's an easy calculation. But notice the confidence level that it has in, which is essentially what a machine learning model is going to solve for, right? Quality, time, and price. And we're going to get into how you quantify all those things. All right, so now let's move away from simple resource usage, and we're going to figure out how to quantify quality, right? Like, what's quality, image quality? And it's easy for a human or an artist to look at something, but it's not easy for a computer to look at an image and say that is a high quality image. There's a lot of cool stuff that NVIDIA's been doing with optics to do smoothing and based on machine learning, which to me is just magic, and well, obviously to Kevin too. But I don't know a whole lot about the algorithm or what's going on under the hood, and I assume that it's some pretty complex stuff. But I'm actually working with some engineers at Google on transcoding. Transcoding, if you don't know, is just taking a video in one format and converting it to a video in a different format. But it's a big business, because Netflix, Hulu, YouTube, everybody needs to transcode, because you upload a video in a certain format, has to follow conventions to stream out to the world. So we're trying to determine how to automate the checking of the results. And there's a sort of a basic, this PSNR, the peak signal to noise ratio factor, that is as a metric to gauge whether an image is of high quality enough. And it's almost as simple as taking two images and taking them in Nuke and doing a diff on the channels, right? To see how much the images differ, because you take the source, you take the destination, or the result, and then you diff them. But that result is the peak signal to noise ratio. So if you look at the numbers down at the bottom, like let's say this image is the base image, and these are two separate results, and you could see why. Like this guy, his noise threshold was set higher than the base image, and we've clamped the render time at 1 minute, so it's got a low PSNR. Again, these numbers are just faked, but just to conceptualize. And then if you set the max render time, I was going to set that to 0 to make it unlimited, which everybody in the V-Ray world knows is unlimited. But the lower noise threshold, it takes longer, but it's got a higher score, PSNR score. So a model would come up with that result, and then you could define a threshold and say, reject any image or any frame that's lower than 0.98 or something like that. And to do something like that, you change the quality slider, right? Like, don't give me anything less than a certain amount. And unlock time and unlock price, and obviously you probably want to lock price. That wouldn't be very smart, but we'd provide stopgaps for that. So what happens? obviously, over time, you can refine this, and you can, with every iteration, it can learn again and again, and it can store this data over and over, and your iteration cost goes down. And that's pretty simple to understand that you're paying less over time. The paradox is that you want your artist to go through as few iterations as possible. So that's your mileage may vary. But in this case that we saw before here, now we're going to lock down quality and we're going to lock down time, and then price is the variable here, right? So as you iterate, the price is on a sliding scale. All right, so in my eyes, the previous section is a sort of an easier problem to solve because you're basing it on statistics and existing still image models. But now let's step outside of the realm of reality for a second, and let's look at how we can train. And this is V-Ray specific almost. Let's look at how we can train a model to understand and predict how long a render is going to take. Like, let's forget about looking at just numbers from past data. Let's explore what we have on hand to create a model and to train a model and to get results. So actually, let's go back and we're going to look at 4 different scenarios here. Historical data, which is like logs, render logs, stats, and any type of output that you get from running a render. Render parameters, pretty simple to understand, just anything in the render globals or whatever the render settings are. There's what we call consider scene data or VR scene or a RIB file or an ASS file or whatever, which is generated at render time. And there's also render output, which we're just going to call images themselves, or even elements, which may or may not be a full scene. They may be just a single asset rendered. So let's look at the pros and cons of each scenario. A log file is pretty simple, but they kind of vary depending on what level of verbosity you have and your naming conventions and how well the logs have been stored and how much you have. Typically, to train a model, you need at least 100,000 samples, right? And if you're a render service, that's great. But like, for example, Google acquired a company called Zinc, which some of you might be familiar with. It's render farm as a service. But we can't just take all the render logs from everybody's usage because of privacy concerns, number one. Number two, I don't think we keep them longer than 90 days or something. So do we have 100,000 records? Maybe. A large facility like an ILM or an MPC or a frame store would have hundreds of thousands of these logs that they probably keep for years back. So log file data can easily be mined and can be understood and parsed. Scene data. Now this is a little bit more. This is actually a better way to capture data because you're basically. It's almost as if your machine learning model is a renderer, right? Like it's ingesting your VR scene and it's saying, okay, this is the camera. These are its settings. These are the materials, and these materials have certain settings. And here's the geometry. Maybe you can sort of parse the geometry and the lighting and everything. And then it'll take all that data and it'll be able to understand the contents of it. But again, this needs an output. So like the log file, you would need to associate it with a final image and the final stats. So like this VR scene file at this particular frame took X number of resources to render, and that's the training data right there. And you need lots and lots of those again. So that's scene data. Render parameter data, there's probably people out there doing this now, sort of, even throwing up flags to an artist like, oh my God, you set your quality settings way too high. This will take way too long to render. But I think one thing that machine learning today is very good at is just understanding input numbers and providing output numbers. So if you take a value like, well, not max render time, that's too simple. Like a noise threshold is probably the standard metric, right? You could correlate noise threshold with render resource usage. And then you could build a model around that. And you could do that for every render parameter. It would take a while, but you could automate it, and you could come up with a really good set that as you dial in your numbers, you could have a the results, the predicted results, as like a dashboard that would show you exactly as you change your sliders, it's going to take longer or shorter to render. It's going to use whatever resources, stuff like that. And then the final structure for how we could build a model is actually taking the render output, and this is kind of the most interesting type of machine learning, which is image-based machine learning. But you're basically training a model to understand what it's looking at. And one of the things that I put in here one of the major cons is that it's this cart before the horse, meaning do I have to do a render in order to train it to understand how long it's going to take to render? Well, that's crazy, right? Well, hold on a second. What if you just do a PrePass, right? Or like an initial illumination or radiance map or something that only takes a couple seconds, right? Like maybe for a huge scene it might take minutes, but can you take this really, really noisy data and extract information from it that you could have a trained model say, oh, this is a couch. I know how long this asset takes to render, and I know what kind of resources it requires. So, this is pretty cool stuff, but you need to be able to train a model to sort of spatially understand what's in the frame, and you also need to train it on your asset database. And this is where we get into deep neural network, in that, okay, so you have instead of a number, you have an image. And this couch image, sofa, I'm sorry, I'm Canadian. The sofa would get broken down into more than 786 pixels, but it doesn't matter the number of pixels, I guess, because the resolution of the understanding of the render is sort of arbitrary. But then you could step down through the different layers and compute CPU usage and therefore time and memory. So I contributed to a solution that's on our website, which basically takes a set of geometry and performing a bunch of automated renders. You just render like take a single object and you render it from thousands of angles, and you take those images and you train a model to understand what that image is, right? So that then you've got this object that could be in any lighting scenario, from any angle, from any lens, any sort of like lensing or any interior, exterior scenario, whatever, and it'll be able to identify it. And this solution actually comes with this kitbash set you could see behind on the left-hand side. There's like 512 pieces that you can download, and you can actually go through this tutorial of training a model to understand, 1 or 3 or 200 of these objects. And it goes a little bit beyond that, because it uses like it goes into the IoT world, where you actually build a Raspberry Pi camera, and you 3D print one of these objects, and you take an image, you take a picture of the 3D printed object, and it recognizes it. So it's super helpful in the engineering world, obviously. Like you're an airplane engine mechanic, and you open up the cowling on the side, and you've got these AR glasses, and you can identify all the pieces of the airplane engine. Like that's sort of my big idea for how this could all work. But basically, you've got this 3D geometry. Why not use it to train a model? That's pretty cool. It's been done in 1991. Oh, well, it hasn't been done, but it's been conceptualized by James Cameron. I mean, it's kind of like similar type of thing here. But look, he achieved 99% probability, so why can't we, right? It sort of goes, now you get into the convolutional neural network of building and capturing 3 different kinds of data. You've got lighting and texture and render settings, and like you can sort of cross-relate all of those, and you could supply let's pretend this was that sofa in low res. What it's going to do when it gets to this CNN, this convolutional neural networking, is that it's going to, almost like voxels, it's going to perform a step function all over the 2D image, and it combines the flat and the layered stacks to come up with a prediction. And you could provide it with different identifiers. One of the ideas I had was this is based on particular shaders of a car model. So where it's shiny paint, it sort of has a different understanding of what the tolerance and the resource usage is for, super shiny paint or transparent glass. There's, the refractivity is going to, cause different results in predictions, and the chrome wheels or the flat rubber of the tires, would sort of provide a different or force a different type of model computation. So, using all this different information, can you take it to that extent, and can you predict that type of resource usage? So, one last thing, and that's basically this would be your user interface, right? Just give me another flag, turn training on for my renders, and leave it on for the next 6 months or something until you have a trained model. So, wouldn't it be cool if you could? And I'm not saying that Chaos Group is going to do this, no promises, but wouldn't it be cool if you could just turn on training and build your own model at your own facility or in the cloud through, we've got all these TensorFlow as a service, and you could build your model remotely and do all the computation on different GPUs or TPUs. But anyways, you just turn it on and it just starts to work. And sort of a pseudocode for all this could be, taking all the data from things like the render view or the lighting information or the geometry information, and all that data is not only streamed to the viewport or to the render buffer, but also to a model that's ingesting this data for training. And it would sort of learn at the exact same time that it's streaming, and that the render would be done, and the model would gather the render information and would be trained immediately. So that as you the more you render, the more it's going to understand. And then you turn training off, and you access the API for that model that would allow you to grab that information and run your predictions. And you've got this framework for reducing or estimating your resource usage.